Being recorded.
So this is a discussion on the material in section 4.3. We'll have a quiz on this on Thursday. So one thing too is the second half of the course, maybe you might have already noticed, is it's harder than the course just gets increasingly more difficult. I think the first fourth was probably definitely chapters 1 and 2 are the easiest parts of the course. Then we had chapter 3, but yeah, I think the hardest material is in the second half of the course, and so it just goes fast. I mean, but you probably realize that. So we're going to talk. There's a lot of material I think in this section. We're going to talk more about how we can find a relative extreme, or maximum and minimum points just by looking at derivatives. We're also going to talk about functions being, concave down and concave up. So here's just an example. So I think of a concave down as like it's like an upside down U. So like here, this part here would be like concave down. And then so here, then it goes, and then at this point B, it goes concave up. So concave up to me, we'll talk more about this later on. Concave up is more like it's like a normal U. So or something like I think it was like a concave down is an upside down cup. The water is pouring out. I don't know why I think of it that way. And then concave up is a cup where you're holding the water. Okay, so and okay, so let's just review a few facts right here. Okay, so let's say we have some interval a b, and the first derivative is positive. That means the slope is going up, right? So the function's increasing, right? So as we move from a to b, the second coordinate just gets bigger and bigger and bigger. And so in contrast, if the second derivative, I'm sorry, the first derivative of a function on AB is always negative, then the slope is going down, and so the function's decreasing. So if we start from A and we go to B, the graph would be going down. Okay, so then here's what we call the first derivative test. So let C be a critical point. So remember that's where the derivative is zero, right? Or if the derivative doesn't, or where the derivative doesn't exist, like an absolute value function. Okay, so if f of x changes from positive to negative, then f has a relative maximum, right? Positive to negative, right? And so then we have this maximum right here. And in contrast, okay, so if f of x, so let's say to the left of the critical point, the derivative is negative, and I think this should be positive here. And then yeah, so if f of x changes from minus to positive, then x has a relative minimum, right? So if it goes from negative to positive, and here's our critical point, so then we have a relative minimum, right? So yeah, so if to left of the critical point the derivative is negative, and to right of the critical point the derivative is positive, then we have a minimum. Then vice versa. So then if to left of the critical point the derivative is positive, and to the right the derivative is negative, then we have a relative maximum. So that's the first derivative test. So that's one, and then we're going to talk about something called the second derivative test, which I think is actually a little bit easier to use if it's applicable. Yeah, so first derivative test, so in the last unit we learned that if you have a critical point, if you want to know if you have a relative or absolute or relative minimum or maximum, you just make a chart, right? You find all the critical points, and then you evaluate the function if it's on a closed interval at the endpoints, and also at all the critical points, and then you just inspect, which is the biggest and which is the smallest. But here we can actually tell whether if you're a relative extreme or relative minimum or relative maximum. So that's actually kind of, and I have an example. There's lots of examples in here. So I took some from the homework here. Okay, but let's just look at what we have right here. So we have this function, and I don't know if you can see it here. Maybe I can. Okay, maybe that's a little bit better. Okay, so let's look at this function x cubed, and this is actually this file is online. You have x cubed minus 6 in this polynomial 6x squared minus 38x plus 240, and so let's just find where the derivative is increasing and where the derivative is not increasing. So it turns out hopefully the derivative of this function is relatively easy because it's just a polynomial. And so we just use the power rule to find out the derivative. So it's 3x squared minus 13x minus 38. And we're going to solve that. We want to find the critical points. So find where the derivative is 0. And it turns out it's at 19/3 and -2. The thing is that the derivative is a continuous function, right? We cannot, meaning that we can draw without lifting our pencil. So that means that in between the critical points, like from -2 to 19/3, the derivative function, if you actually graphed it, would be totally above, it'd be totally positive or totally negative, right? Because if it crossed the x-axis again, you'd have another critical point. So let's just see where the derivative is. So the critical points will divide the real number line up into segments. Where, and this is an important point. We find the critical points, and that divides the real number line up into segments where the derivative is positive or where the derivative is negative. Okay, so now how do we know where? Let's look at to the left of -2. And you can see there, like it says here, to the left of -2, positive, and then we have negative in between -2 and 19/3, and then to the right of 19/3, the derivative is positive. All you have to do, so this is the great thing, all you have to do is evaluate the derivative at one point in that interval. Like if you plug in -3 into the derivative function, this 3x squared minus 13x minus 38, you plug in -3, you're going to get a positive value. Now let's say you plug in 0. So let's say you plug in 0. So that's a number in between -2 and 19/3. When you plug in 0 into the derivative function, like f prime of 0 is -38. Okay, so that means that the derivative function is negative everywhere between -2 and 19/3. Again, if it was both positive and negative, because when we plug in 0, f prime of 0 is negative, right? It's negative. It's -38, and so we can again. I'll just emphasize this again. We can claim that the derivative is negative everywhere in between the critical points -2 to 19/3, because if the derivative became positive somewhere in between -2 and 19/3, there'd be one more critical point, but there isn't. There's only 2 critical points. And we get that from solving the equation f prime of x equals 0. Okay, so again, so just to summarize, how can we determine where the derivative is positive and negative? You find the critical points, and those critical points either divide your interval. We'll divide your interval up into segments. And we just take one point in each of those segments and we determine, is the derivative positive or negative? And that's how we can tell in each segment, in between each critical point, whether the derivative is positive or the derivative is negative. So here what you can tell is in -2, the derivative is positive to the left of 2 and negative to the left of negative. Let me say it again. To the left of -2, the derivative is positive. To the right of -2, the derivative is negative. So -2, the critical point of -2 is an extreme, is a maximum, right? The graph goes up to the left of -2 and goes down to the right of -2. And it's just the opposite with -19/3. To the left of 19/3, the derivative is negative, meaning the graph is going down, gets to, right? And actually, here's the plot right here, right? So here's 19/3. So yeah, so the derivative is negative to the left of 19/3. The graph goes down. It gets to 19/3. So there's this horizontal tangent point, and then the derivative, then the function changes directions to the right of 19/3. The derivative is positive. The graph starts going up. So 19/3 represents a minimum. So let's look at another problem right here. Unless there's so many problems here. It's not really. I don't think we want to go over all of them. But here, let's try this one. Hello. Okay, so I took this from the homework. I think this is problem number 10 in the homework. Okay, so we have this function here, -2 times cosine of x minus x, and it's going to be defined on the closed interval 0 to pi, and we want to find the intervals in which f is increasing and the intervals in which it's decreasing. Okay, so again, our solution is first find the critical points in the interval 0. Again, our domain is restricted to 0 pi, so find the critical points of this function f of x in from 0 to pi, and then we'll use those critical points to divide 0 into pi into segments, and then we'll see is the derivative positive or to the left of or is the derivative positive or negative on either side of the critical points. Okay, so let's actually just start the problem. It'll be easier than just describing the algorithm. Okay, so first we're going to solve. So if f of x is this function right here, 2 minus 2 cosine x minus x. And so we want to know where f prime of x is 0 on the closed interval 0 to pi. So f prime of x, that's kind of set up nicely. Yeah, so derivative of cosine is minus sine. So f prime of x is 2 sine x minus 1. So we want to find where that is 0. So we solve the equation 2 sine of x minus 1 equals 0, or sine of x is equal to 1/2. And then, hopefully we love trigonometry so much that we know that the second coordinate, if we go pi over 6 radians or 5 pi over 6 radians, we know the second coordinate is 1/2. So we know the solution to sine of x equals 1/2 is pi over 6 or 5 pi over 6. Okay, so the critical points are pi over 6. So the derivative of minus 2 cosine x minus x has the critical points pi over 6 or 5 pi over 6. So that's where the derivative is 0. So those are the potential extreme points. Okay, and so the critical points 5 pi over 6 and 5 pi over 6 will divide this segment 0 pi into the following open intervals: 0 to pi over 6, pi over 6 to 5 pi over 6, 5 pi over 6 to pi. And we want to know is the derivative positive or negative in these segments? And again, it can't be both, right? Because the derivative is actually a continuous function. When we draw it, we don't lift the pencil up. So the derivative, when we graph the derivative, it can't, if it goes from below the x-axis, if it goes from negative to positive, that means there'd be another critical point. So there can't be critical, so the derivative must either be totally positive or totally negative in these open intervals. And if that's not true, then there's actually one more critical point. But there isn't, right? The solution to this equation tells us all the critical points. So the great thing is, okay, we find the critical points. We use the critical points to define our, divide the interval of interest into segments. And then all we have to do is take one point in each open interval to determine if f prime is negative or if the derivative is positive or negative. Okay, and it doesn't necessarily, and again, what point do you pick? You pick points that I think are convenient if they exist. Okay, so like from 0 to pi over 6, well, I don't really know any convenient points. So I said, okay, I know, just make sure that the point you pick is in the interval. Okay, so I know that pi over 12 is in between 0 and pi over 6. And I use the calculator. I don't actually know what sine of pi over 12 is off the top of my head. There's no exact answer. You can use these, there are formulas for that, but let's just use your calculator. And it turns out it's f prime of negative 12, 2 sine of pi over 12 minus 1. Well, it turns out it's about negative 4.8, so it's negative, right? So we know that the derivative is totally negative from 0 to pi over 6. And now let's look at the interval, that second one, pi over 6 to 5 pi over 6. Let's use one of our favorite numbers in trigonometry, pi over 2. And so we know that f prime of pi over 2 is 2 sine of pi over 2 minus 1. Well, sine of pi over 2, see, that's a convenient number. Sine of pi over 2 is 1. Okay, so and so we get 2 minus 1, we get 1. So the derivative from pi over 6 to 5 pi over 6 is positive. Okay, well, and it's amazing. All we have to do is evaluate at one point. And then now let's look at the interval to the left of 5 pi, to the right of 5 pi over 6. And now we'll use 11 pi over 12. And yeah, because 5 pi over 6 is 10 pi over 12. So let's look at halfway in between 5 pi over 6 and pi, which is 11 pi over 12. And we evaluate 2 sine 11 pi over 12 minus 1. It should be the same as the pi over 12. And once again, I get negative 0.48. And so, so now, yeah, to the right of 5 pi over 6, the derivative is negative. So it's negative. We get to pi over 6, it goes to positive. And then we get to pi over 6, it goes back down a negative. Okay, so so basically that actually answers that would actually answers the question. So f is decreasing from 0 to pi over 6, and then it's increasing. So pi over 6 would be a relative, right? It's going down and then going up. So pi over 6 would be a minimum. And then at 5 pi over 6, you're going from positive, and then it starts going down. So 5 pi over 6 would be a maximum, and that's the first derivative test. I think it's more than what the question is really is asking. I think let's go back and see what the question is asking. It's one of these multiple choice problems that I never really get wrong the first time because I'm not actually reading the problem carefully. Okay, so you got these 4 choices. So well, we know, well, we did some work here, so we know the function is never increasing. So it can't be A. We know the function is increasing and decreasing. Yeah, so the function is never decreasing. We know it can't be C. The function is never increasing. That'd be some kind of crazy function. The function is never increasing or decreasing. I don't know that can be true for a continuous function. Okay, so it's actually on this option B. And then, yeah, so and then I think we actually found that it's increasing, was it, what did we say, pi over 6 to 5 pi over 6? And decreasing on the open intervals is at 0, pi over 6, and then 5 pi over 6 pi. Yeah, sorry, my handwriting. I'm writing vertically on the screen. It's a little bit hard for me. Okay, but anyway, I think you actually get the how to do this problem though. Again, you take the derivative, you find the critical points, you use those critical points to divide your interval up into segments, and take 1 point from each of these, these open interval segments, and determine is just plug the number into the derivative function, see if it's positive or negative, and that tells you whether the derivative is negative or positive throughout that interval. And then the first derivative test is, if you're going from negative, if the derivative is negative to the left and positive to the right, you have a minimum. And if the derivative is positive to the left of a critical point and negative to the right, you have a maximum. Okay, so I think we're done with that interesting part of this. So it's actually, yeah, first derivative test. Okay, yeah, okay. I'm going to tell you the second derivative test is my favorite. We haven't gotten there yet. Okay, so so don't turn the video off until you get to the second derivative test. Okay, so let's see here. Where are we here? Okay, so there's some more of these. Okay, so let's go to the exciting part here. So these are just more examples here, they're all the same thing. They're all based on the same example: finding the derivative, finding the critical points, using the critical points to breaking the interval up into different segments. Okay, so let's get to and then there's a word problem here that I'm not going to talk about. So let's talk about concavity. Okay, so I did one example, a couple of examples using the first derivative test. So I didn't do all the examples in these notes, but you're always welcome to ask questions. Okay, so now remember we've already kind of talked about concavity because I started with it because I like concavity so much. Okay, so anyway, okay, so concave up, concave down. So you always think again, it's the upside down U or the normal U, or I mean normal U, the U that we normally see, the one that's right side up. So I think is it an upside down cup that's spilling water, or a right side or cup that's holding water? So the upside down cup or the upside down U is concave down, and then the normal, the U that we normally use in our writing, that would be concave up. Okay, so let's say F. Let's look at where it's concave down. See F. Now F prime is actually decreasing. See where it's concave down. So let's look to the left here. So of this maximum point. So you said that the graph is actually going up. You see it's kind of slowing down. It's decelerating, right? It's just slowing down. So that it's still going up, but the slope is becoming less and less steep till finally the slope becomes 0. Oh, and now the graph starts going down at a faster and faster rate. So the derivative function is actually decreasing, right? The slopes are decreasing. So it might be like, even though the slopes might be positive, the slopes are decreasing. If you actually graphed it, if you graphed it here, the graph of the derivative function would be above the x-axis. And here, the graph of the derivative function would be below the x-axis, but it would be going down. So the slope of the slope of the derivative function is negative. Okay, so in other words, so the slope of the slope or the slope of the slope is the second derivative, right? You're taking the derivative of the derivative. Okay, so when f prime is decreasing, that means the second derivative is negative, and the graph is concave down, and it's just the opposite. So here, let's look at to the right of this red point right here. That's actually called a point of inflection, where we go from concave down to concave up, or vice versa. When the concavity changes. Now see here, you can tell to the right, well, the slopes are still going down. I mean, if we were graphing the derivative function, the graph would be below, it'd be negative, it'd be below the x-axis, but what it is it's getting less and less, it's going down at a slower and slower rate, till finally we see here, the slope just becomes zero. And then all of a sudden, the slope starts becoming positive, right? And it's going up and up at a faster rate. So to the left of this minimum point right here, right, to the left of that, yeah, we see the slopes are going down, but it's slowing down. So it's not going down. It's not decreasing. It's decreasing at a slower and slower rate till finally we get a horizontal tangent line, and then the graph starts going up at a faster rate. So the first derivative, the second coordinates are actually increasing, even though they initially might be negative. If you actually graphed it, the graph of the derivative function would be going up. To the left of this minimum, the graph is below the x-axis. To the right of that, of this point right here that I keep drawing on, that minimum right there, the derivative function would be above the x-axis. Okay, but anyway, f prime is increasing, right? Because to the left of that, to the left of this minimum point, the derivative is decreasing but at a slower rate, and to the right of this minimum point, it's increasing at a faster and faster rate. So the rate of change of the derivative is positive, right? The derivative of the derivative is positive. So when the second derivative is negative, it's concave down, and when the second derivative is positive, the graph of the function is concave up. So the second derivative can tell us, something about the shape of the graph, right? It tells us whether the graph is concave up or concave down. And then we're eventually going to use that fact for the famous second derivative test, which it's really a very popular test. Okay, so if the second derivative is positive for all x in some interval a b, then the function is concave up, and so you get the kind of this kind of U-shaped graph. If the second derivative is negative for all x in a b, then the graph is concave down. So that means that the graph could be going up, but it just goes when it's concave down, the graph could be going up at a slower rate. Okay, so the point of inflection is where the concavity changes, and that's where the second derivative. So the second derivative would be zero, where at the point of inflection. So the point of inflection, if you're going from concave, like here, we're going from concave down to concave up. So at the point of inflection, the second derivative is negative. I mean, when the graph goes from concave down to concave up, the second derivative is zero, right? When you change concavity, the second derivative is zero. So let's look at this one function. Actually, is this the one I wanted to do? I graph something right here. Okay, so let's just look at let's just look at this. Let's look at one more example before we get to the second derivative test here. There's one. I actually added a graph to these notes here. Okay, so let's just look at example 7. That's a relatively easy problem here. So we have this polynomial x cubed minus 5x squared minus 8x plus 5. So we want to find where the function is concave up and concave down and locate any points of inflection. So again, you're going to have to compute the second derivative. Okay, so we have to do this. The polynomial functions are favored because it's easy to kind of get the second derivative. So when you start getting these messy functions, you have a product and you have to use the product rule, and then you have to take the derivative again. Yeah, or if it's a trick, it can get kind of messy in some of these. But here's this one's kind of, this problem example 7 is our friend. Okay, so the first, you have to take the derivative twice, so use the power rule. So 6x squared minus 10x minus 8. And let's see here. And then you take the second derivative. Oh, and it turns out there's only going to be 1 point of inflection. So the second derivative is 6x minus 10. And you saw, so where is the second derivative of 0? It's 0 and x equal to 5/3. Okay, so then 5/3 is going to break, the real number line up into 2 pieces. And there can only be 1 point of inflection, right? I mean, there can be more than 1 point of inflection, but just based on this, the second derivative, there's only one place. You saw that equation. You get you only get one. There's only one place where the second derivative is 0. But in general, yeah, there could be many points of inflection. But for this particular function, there's only 1 point of inflection. Okay, so where is the second derivative positive and where is the second derivative negative? So again, you can just take 1 point on each. So 5/3 divides the real number line up into 2 pieces. So let's see, and all you have to do is take one number on either side and evaluate the second derivative. So like you plug in 0, right? So that's to the left of 5/3. So f double prime of 0 is -10, right? Yeah, let me see if I can do that a little bit better. F double prime of 0. So it's negative, and so that means it has to be negative everywhere to the left of 5/3. And again, if it was both positive and negative, if the second derivative is both positive and negative to the left of 5/3, that means there'd be another place where the second derivative is 0. But just from our algebra here, we know that that's not possible. And then you take a number to the right of 5/3, let's say like 10, and you plug that into the second derivative function. F double prime of 10 turns out to be 50, which is positive. Okay, so to the left of 5/3, the second derivative is negative, which means to the left of 5/3, the graph must be concave down, and to the right of 5/3, the graph must be concave up. Here, let's just look at another problem here, and then I have one more homework problem that I tried, and that we'll look at here. Is this okay, I added to these slides here. Okay, so yeah, okay, so let's see here. Okay, so so this is where I added to the slides. Okay, so find all relative extrema for, okay, so here's another, it's kind of like the other one. I guess, polynomials, we x cubed, and I forget the coefficients after all polynomials. Have I seen this one before? Okay, so anyway, find all relative, students, so sorry, I'm jumping the gun here. It's the second derivative test. Okay, so here I talked about how much I like the second derivative test, and here I'm just about ready to skip it. I wonder what that means. Okay, anyway, second derivative, we had the first derivative test, right? First derivative test is used to tell if we have a relative extreme. We find the critical points, and we looked on either side of the critical points to determine whether see where the first derivative is positive and negative. That's a little bit, this takes some work, right? Not that much work, but it takes some work. But the second derivative test, okay, so we find the critical points, and then we find the value of then we find what is the value of the second derivative of the critical point, right? So the critical point, that's where our potential minimum or maximums are, okay? Okay, so let's say we have a critical point C, and the second derivative is negative. Well, you have to have a maximum, right? So remember, because if the second derivative is negative, that means the curve is concave down. So here's f prime of C. It has this horizontal slope, and the curve is concave down. It's got to be a maximum. And now let's say we have some critical point C, and the second derivative is positive, right? So that means the curve is concave up, and C is this critical point. So we have this horizontal slope. That means we have to be a minimum. Now here's the thing, students. F double, let's say we have a critical point C, that means F prime of C is 0, and the second derivative is also 0. Then the test is inconclusive. We may not have an absolute minimum or a maximum, right? So the famous example is, I think, like for here, for 3, is f of x equals x cubed. And if you graph the function, see, so it's 0, let's say f of x equals x cubed, the first and second derivative is 0 at 0, right? So 0 is not a relative min or a relative max, right? So the second derivative test only works if the first derivative is 0 and the second derivative is not 0. But if both the first and second derivative are 0, you're going to have a point of inflection, but you may not have a relative. It may be a point of inflection. Let me say it again. If the first and second derivative are 0, and that critical point C just might be a point of inflection instead of a relative min or a relative max. Okay, so let's look at example 9 here. Okay, so we're going to find all relative extrema for this polynomial here, one of my favorite polynomials, x cubed minus 5x squared plus 7x. And okay, so let's first find the critical points, right? So we're going to find the critical. So for this example 9, we're going to find the critical points, and then we're going to determine. Then we're going to find the value of the second derivative at those critical points. Okay, so so we take the first derivative, and we find the first derivative. Use the power rule. 3x squared minus 10x plus 7. So the problem was set up in such a way that it can be factored easily. So we find the roots of So to solve f prime of x is 0, we factor that polynomial. We get 3x minus 7 times x minus 1. And it turns out the critical points are 7/3 and 1. Okay, so you can use the first derivative test by just finding where the derivatives are positive and negative. Okay, but we want to look at the second derivative test. So the first derivative test, okay, you plug in a point, 1 7/3 divides the real number line up into 3 parts, and you take a point to the left of 1, you take a point in between 1 and 7/3, and you take a point to the right of 7/3, you plug it into the first derivative function, and you see is the first derivative positive or negative everywhere in that segment. So we can see here to the left of 1, the first derivative is always positive. In between 1 and 7/3, the first derivative is always negative. And then to the right of 7/3, the first derivative is positive. So 1 has to be a maximum, and 7/3 would have to be a minimum, right? Because to the left of 1, it's going up, and to the right of 1, the graph is going down. Now let's use our friend, the second derivative test. And the first derivative test is also our friend. Okay, so anyway, okay, so we know the critical points again. So we're going to use this. We just use the first derivative test to determine the critical points of that polynomial x cubed minus 5x squared plus 7x. Are those minimum or maximums? Now we're going to use the second derivative test. So we already have found our critical points, 7/3 and 1. Now let's evaluate the critical points. Now let's evaluate the second derivative at the critical points. Okay, so we take the derivative of 3x squared minus 10x plus 7, and we get 6x minus 10. Okay, and so the second derivative at the first critical point 1 is negative, right? So it's got to be a maximum, right? It's concave down, right? So the second derivative at 1 is negative. The curve must be concave down. So we have a maximum. And the second derivative at 7/3, we plug that into 6 times x minus 7, and it turns out the second derivative is positive, so the curve is concave up, and we must have a minimum. Now this is what I actually added to the notes that I originally posted online. I actually graphed the function, and so there you can see. So we can see that the critical point 1 is a maximum. So f prime of 1 is 0. So we have this horizontal tangent at 1. And f double prime of 1 is negative. So we have it's concave down, right? See, it's that down, upside down. Water would fall. If we turn the cup over, the water would fall out. Here at 7/3, once again, yeah, we have this horizontal tangent, and the second derivative is positive. You can see the curve is concave up. So that's the famous second derivative test. So students, if it was me, and I'm just speaking for myself, I would always use the second derivative test before the first derivative test, unless the problem explicitly says use the first derivative test. Because I do remember the last time I taught calculus, it seemed like a long time ago. Sometimes I would put problems on the test. I use the first. I wanted the students to demonstrate their knowledge of the first derivative test, and they would use the second derivative test. Well, of course, I have to mark it wrong. Okay. Yeah. So okay, students. This is getting kind of long, I guess, but this is why I made the quiz. The quizzes were originally going to be 4.3 and 4.4, but 4.3 has just got a lot of stuff in it. Okay. So let's just look at one more problem here. And okay, so now let's just determine the intervals on which the following function is concave up or concave down. Identify any inflection points. Now this function here, this is problem 24 from the homework. Yeah, 24 from the homework. Well, first of all, it has a vertical asymptote, right? The function's not continuous at t equal -4, right? The denominator is 0. So it's actually going to be some kind of like hyperbola shaped curve. With the vertical asymptote at t equal to -4, and so let's see here. So then we also want to identify any points of inflection. Okay, so first of all, we have to take the second derivative. That seems kind of painful, doesn't it? Maybe not. Let's see. Okay, so we know the function is it's just linear functions. And the coefficients are the same. Here are the same in the numerator and the denominator. So they're kind of nice to us. It turns out after we take the first derivative, it actually becomes a little bit simpler. So we give t plus 4, that's the denominator, times the derivative of t minus h, which is 1, minus t minus 8 times the derivative of the denominator, which is 1, and then divided by the denominator squared. Okay, but you see how the t terms drop out? So it's actually, the numerator is 4 minus 8, which you get 12. So the first derivative is 12 over t plus the quantity t plus 4 squared. One thing is, yeah, we know that the first derivative is positive everywhere. Okay, so now let's find this, but we want to find the second derivative. We want to know where is the graph concave up and where is the graph concave down, which means we have to look at the second derivative. Okay, second derivative. Well, now it's a little bit easier. It's not a quotient. We can just use the power rule. And what is a quotient? 12 over t plus 4 squared. But we can use the numerators as a constant. So we'll use the power rule. Look at negative. We drop down the -2. -2 times 12 is -24. And subtract 1 from -2, you get -3. So you get the second derivative is -24 over t plus 4 cubed. Okay, well, t plus 4, well, the numerator is always negative. Okay, so you cube something, you cube a negative number, you get negative, right? So let's see, when you get negative over negative is a positive, and positive, let me say it again. Negative over negative is positive, and negative over positive is negative. It turns out there's actually no points of inflection. There's no point where we get 0. Okay. So let's see. So t plus 4 is positive when t is greater than -4. Okay, so negative over positive is negative. So the second derivative is negative when t is greater than 4, when t is in the open interval -4 to infinity. And when t plus 4 is less than 0, when t is less than -4. So negative divided by negative is a positive. So g double prime is positive for t in the open interval negative infinity to -4. Okay, so remember what we said. Remember what we said, that the graph is concave down when the second derivative is negative, right? So in this interval here, -4 to infinity, the graph would be concave down. And the second derivative is positive from -infinity to -4. So in this interval, the curve would be concave up. And there's no points of inflections, because if you actually tried to solve this equation, -24 over t plus 4 cubed, there's no places where that function is 0, right? And I think I actually graphed it, right? So here's the graph, right? So remember what I said? So for t less than -4, yeah, for t less than -4, the curve is concave up. See, this is concave up. Right? F double prime is positive there. And here, for t greater than -4, the curve is concave down. Sorry,